Okay, hello guys. So this first video will be to try and understand how we can represent traveling waves using graphs, right? We've talked about the variables that we can use to describe them, like period, frequency, velocity. We've talked about different types of waves. But there's two types of graphs that we can draw that can give us all the information that we need about waves. So you remember this is the model that we were working with. And if you remember from this model, what we were looking at is the fact that each one of these particles that is along the wave is actually moving up and down around the equilibrium position, right? So they are actually executing what we call simple harmonic motion. Each one of those particles is moving in the same way. If you take this one down here, you will see that it eventually comes to the equilibrium position. It goes up to the same point, and all of them, regardless of where they are at this specific instant of time, they're all in the process of doing that simple harmonic motion up and down cycle. Okay, so because there's a lot happening, right? Each particle is moving, and you can see that also not only they're all moving, but they're all moving in the same way, meaning that they go between the same two extremes, but also they don't do it exactly at the same time. Like this particle here is, well, there at that point, and it will eventually get up here, but it will be a different time for this other particle here. And it's like each individual particle has its own time to do the things, but they will all do the same at the end of the day. So because again, I was saying there's a lot happening. What we usually do is when we're analyzing waves and when we're trying to describe how waves travel and how waves can be described, we use two types of graphs to describe that, because there's again a lot of information and you cannot put everything into just one graph. If you imagine, it would be impossible to put in the same graph what is happening for each one of the particles for every instant of time. You either go with one particle and see how that particle moves with time, or you just look at all the particles but you keep the time fixed in a way. So that will be a little bit clearer and easier to understand once we get to the first type of graph. So everything that I want you to remember for now is our little model here, where we have the wave propagating to the right, and each one of those particles is performing simple harmonic motion up and down. So let's get to the point here. So this is the situation, right? We have this wave, and we know that this wave is actually propagating to the right in this direction. Let me make this a little bit thinner. Okay, so it's propagating. This is the direction of propagation of the wave, and we know that the vibration is perpendicular to this, which makes this what type of wave? I guess you're right, I don't know, but if you thought that this is a transverse wave, then you are correct. That makes this a transverse wave. And the first type of graph that we're going to analyze, or the first type of graph that we use to describe a traveling wave, and this is not only for transverse waves, this is also for longitudinal waves. The first type of graph that we're going to look at is the displacement versus time graph. Now, what exactly is a displacement versus time graph? Well, it's a graph where on the vertical axis you're going to have the displacement, and in the horizontal axis you're going to have the time, right? Now, what exactly are you representing? This displacement versus time graph shows you the motion of one and only one particle in the medium as time passes, right? And then there's no surprise that we're saying that it's a displacement versus time graph, because it's actually showing you where the particle is, right? It's showing you displacement with time. Now, there's a lot of particles here. Which one are we going to choose? It doesn't really matter, because if you remember, they will all move and do the same. They will do it at a slightly different times, but they will do the same. So if I want to represent the motion of, say, I don't know, the first particle, right? What is the first particle doing? So at this point, the particle is at the equilibrium position, right? When time passes, that particle will go up and then it will go down. Now, that could be the same for this one, right? Just that this one maybe will go down first and then it will go up. So it's going to be different for sorry, each one of the particles, but they're all going to do the same at the end. So the graph, basically, depending on the particle that you choose, is gonna start going up or down. But the point is that each one of those graphs is gonna show you exactly the same pattern, the same behavior. That's a terrible graph, but let's go with that one. And what this is telling you is that this particular little ball, right, that is represented here by that is representing one of the particles in the string, is oscillating up and down with time. Now, how do you call this? Oops, sorry. How do you call the distance between this point and this point? If your answer was that you call that the wavelength, you are not correct, because that axis, that horizontal axis, is not showing you distance, it's showing you time. Now, you need to remember that this graph represents how one particle moves. So this point here represents that at this particular time, let me call it T1, the particle was at the top, right? And then some time later, in a time that I'm going to call T2, the particle was again at the top. So what does that mean? That could be this particle here. Let me just change the color so it's easier to see. This particle here, right, was at the top at time T1, and then it went to the bottom, right? That's what the graph is showing, that it goes down, and then it goes up again, right? And comes back at time T2. Now, let me just get rid of those things. Now, what is the time that a particle will take to start at the top, go down and go up again to the same point where it started? Well, that time is what we call the period. So it's interesting to see that in this graph, that distance between a maximum and the next maximum is actually the period. And the reason is that this is a graph representing just one particle, right? We're not looking at the wave itself, we're just looking at one particle along the wave. Now, what do we call this thing here? This distance between this point and this point. Oops, sorry, I deleted something else. What is this called? And if your answer is that we call this amplitude, then you are right. That is the amplitude, and that amplitude can be found here. And that amplitude actually can be found here in the actual wave, right? Remember, this is like a photo of the actual wave, but here we're just looking at one particle at a time. So if you want to add that to your notes, So this graph looks at only one particle, at different times. And basically I haven't said anything new, I just said the same thing with these two kind of definitions. So this is the first type of graph, right? So in this type of graph, the big takeaway is that this time here that we find between two maximum points is what we call the period. That time could also be found between this point and this point. Well, my graph is really terrible, so this two should be kind of equal because the second one is like very long, but this is the period. Oh, sorry, this is the period. That period could be found also like between any pair of points that you choose that are equivalent. So this point here and this point here, that is the period. You could even find the period by taking just this distance, which will be half a period, and multiplied by 2. Maybe you don't get access to the whole cycle, but only to half of it. So you could actually find it by looking at just half of the period, so the distance between those two. Okay, so let's stop here, and you can ask me any questions you have.